Let's talk about Mercury. As you can see, Mercury is similar to Earth's moon. In our solar system, Mercury is the inner planet closest to the Sun. Due to its proximity to the Sun, it is difficult to observe Mercury. Even the Hubble telescope had safety parameters to avoid the Sun in order to prevent damage to its equipment. As of today, only 2 spacecrafts have ever seen Mercury up close. Mercury is made out of 70% iron and 30% silicate. It has a huge iron core, possibly molten, that makes up about the bulk of the planet. Despite being small in size, it is in fact the second densest planet after Earth and the only solid planet other than Earth known to have a magnetic field. In 2012, NASA confirmed that MESSENGER detected water ice at Mercury's North Pole. As students of astronomy will know, any celestial object that has water is interesting as it might plausibly support life. Recently, another mystery of Mercury has been answered by scientists. Why is Mercury so dark when its elemental composition suggests otherwise? Despite being similar to Earth's moon, Mercury is well known to be one of the darkest objects in the solar system with several dark spots, dubbed LRM. The near side of the moon has several dark spots known as maria. These areas are rich in iron, which acts as a darkening agent. Scientists originally thought that this was also why Mercury looks dark. However, it turns out that Mercury has relatively little amount of iron on its surface. In fact, Earth's moon has much more iron on its surface than Mercury, and yet it is brighter. Another proposed reason is that Mercury collected comet dust from carbon-rich comets. According to modeling and lab simulations, such impact would reduce the reflectance of Mercury's surface significantly. However, they later found that Mercury has a high amount of carbon globally, not just at impact areas. In March 2016, a group of scientists proposed an explanation based on statistically robust observational data from MESSENGER.
MESSENGER is a spacecraft that entered orbit around Mercury in 2011 with 6 primary objectives. The payload on board it includes GRNS. The NS is very sensitive to relative variations in the abundance of iron and carbon, able to determine the elemental composition to a depth of 10 cm by detecting low-energy neutrons resulting from the collision of cosmic rays with the minerals.
Sounds complicated, but how does it work?
To understand this process, it is first important to know what neutrons and gamma rays are and why they are present near Mercury. Neutrons are electrically neutral particles that, together with positively charged protons, make up the centers or nuclei of atoms. Gamma rays are little packets of high-energy lights that are more energetic than the visible lights we see. Both neutrons and gamma rays in the vicinity of Mercury can be produced by the cosmic rays that continually bombard Mercury's surface. Cosmic rays are mostly photons from our Sun or other distant sources in the universe. They easily reach Mercury's surface due to its thin atmosphere. These cosmic rays are moving so fast that, when they collide with an atom, they dislodge neutrons from the atom's nucleus. Some of the dislodged neutrons then collide with the nuclei of other atoms, giving energy to them. When these nuclei return to their normal energy state, they give off gamma rays. Only the neutrons and gamma rays that travel far enough from Mercury can be intercepted by MESSENGER and counted. These measurements tell us what Mercury's surface is made of, as the energy of a gamma ray is a signature of which element this ray came from. So, MESSENGER made repeated measurements and examined NS data acquired over 3 LRM areas. The review increases in thermal neutron count rates that correlate with deposits of LRM. It was able to fulfill the requirements needed to identify graphite carbon as the darkening agent. This agent was derived from a chemically distinct lower crust roughly 30 km below its surface. But due to the disruptive effects of late heavy bombardment and the history of magmatism, source regions of LRM are erratic and of diverse elemental composition. During the early magma Mercurian oceans, graphite was buoyant, forming a layer of graphite crust. Mercury's global low reflectance is a measure of mixing this ancient graphite-rich rust with overlying volcanic materials. Hence, stratigraphic setting of LRM is the best evidence currently that supports an endogenous origin for Mercury's carbon. Given its present surface chemistry, graphite is the only buoyant mineral in any early global magma ocean. What then is the significance of these findings?
This finding suggests we may be seeing remnants of Mercury's original ancient crust that come from the 4.6 billion year old surface we see today. It proves that Mercury has a formation history on its own and is compositionally unique among the planets. It is a testament of the phenomenal success of MESSENGER and adds to a long list of ways the innermost planet differs from its planetary neighbours, providing additional clues to the origin and early evolution of the inner solar system.
Thanks for watching!